Okay, in this video we'll be talking about applying Newton's second law, and we'll be doing it through using a double incline plane. We have two inclines, this incline right here and this incline right there. These angles are both theta, so both of the angles are the exact same. And we have masses on each side. This can be mass m, and this is 3m. These masses are attached by a rope or string, whatever you want to call it, and this is a frictionless pulley. And so as these are going down inclined planes, there is a force going this way. We can call this F1, right? And there's also a force coming down this way, which is F2. There is also tension forces going up the incline, and those tension forces are equal in opposite directions. For this problem, we want to show that the acceleration is equal to g sine theta over 2. So a couple of things we need to take into consideration. First one being we can ignore the pulley as it is frictionless, so there's no effect on the overall net force. Second one being that F1 is equal to mg sine theta, and F2 is equal to 3mg sine theta. Now, if you're not familiar with why the component of weight force down an inclined plane is equal to mg sine theta, I made a video on it, so you can take a look at that and see where it gets derived from. But for this, we'll gloss over it. So if we take our first point and ignore the pulley as it is frictionless, we can redraw this situation as just a straight line diagram, right? So we have one mass here. This is our m. And there is a force pulling it this way. This is equal to mg sine theta, right? This is our F1. And we have a string, which is holding it together. This is this part of the string right here. Again, as the pulley is frictionless, we just ignore it. So there's a tension force going this way and a tension force going that way. But these are these two tension forces right there. This weight is 3mg, and there's a force going that way, that is F2, so that is 3mg sine theta. Right, so we have our diagram now. So here is where we apply Newton's second law. And Newton's second law is the acceleration is equal to the net force applied over the total mass, right? So if we take this side of the equation right here, we go down here, we can say the total forces, which is mg and t, so the total forces acting on the system, over its mass will be equal to the acceleration. So if we rewrite Newton's second law as F net is equal to ma, right, we can construct an equation where we take the total forces and make it equal to ma. So if we define some parameters that positive is equal to the right and negative is equal to the left, then we can say that for this blue equation right here, t minus mg sine theta, again, as positive is to the right, so t is positive and mg sine theta is negative, and that is all equal to ma. Again, this is our net force because we have, these are the two forces acting on this side of the system. If we do the same thing for this side of the equation, we can get 3mg sine theta minus t is equal to 3ma. Again, as this way is positive, to the right is positive, and to the left is negative, we get negative t and positive 3mg sine theta. Now, doing simultaneous equations to get rid of the t, we can add these terms together. The reason why we're adding them rather than subtracting is because one of the t's is negative and the other is positive. So if we add a negative to a positive, they cancel out. Adding these two together, we get 2mg sine theta is equal to 4ma. Then we can divide both sides by 2 to get mg sine theta is equal to 4ma over 2, which can be simplified to 2ma. As both sides have mass on them, we can cancel out the m's to get g sine theta over 2a, and then we get g sine theta over 2 is equal to a. And that is the same thing as above. Okay, moving on to a slightly more complex problem. In this problem, we can see that we don't know the value of the masses, such as m1 and m2, and the angles are different this time. So we have theta 1 and theta 2, and as you can see, that results in different plane angles. This one is clearly more steep than the other. So for this one, we want to show that the tension force is equal to G m1 m2 sine theta 2 plus sine theta 1 all over m1 plus m2. So first things first, we can say that F1 is equal to m1 G sine theta 1 and F2 is equal to m2 G sine theta 2. So again, in this case, the pulley is frictionless. Therefore, we can again draw our diagrams out as m1 and m2. And therefore, as we have tension force and tension force, this is m2G sine theta 2. And this is m1G sine theta 1. And so again, using Newton's second law, which is A is equal to F over M, and therefore F is equal to MA, we can say that T minus m1G sine theta 1 is equal to m1A, and therefore m2G sine theta 2 minus T is equal to m2A. Now again, before we got rid of tension force, but now we actually want the tension force, right? And so what can we see that is not in this equation? That would be our acceleration. So we want to get rid of our acceleration. So how do we do that? We divide, let's call this equation 1, and this is equation 2. So to get rid of the acceleration, we want to divide 1 by 2. And so what we get is T is T minus m1G sine theta 1 over m2G sine theta 2 minus T is equal to m1A over m2A. So as A is on both top and bottom, we can cancel that out. And now to get rid of the fractions, we can cross multiply these. And we get m2 T minus m1G sine theta 1 is equal to m1 m2 G sine theta 2 minus T. Now expanding this out, we get T n2 minus m2 m1 G sine theta 1 is equal to m1 m2 G sine theta 2 minus T m1. Now collecting all like terms, so chucking this over onto this side and this over onto this side, we get T m1 plus T n2 is equal to m1 m2 G sine theta 2 plus m2 m1 G sine theta 1. On this side, we actually have two tension forces when we only want one, right? We only want there to be one. So what we can do is we can take it out as a common factor to get m1 plus m2, just like this. And on this side, we also have m1, m2, g as common factors. So we can also take it out as a common factor. We get g, m1, m2, sine theta 2 plus sine theta 1. Now dividing both sides by m1 plus m2, we get the tension force is equal to G m1 m2 sine theta 2 plus sine theta 1 all over m1 plus m2. And as you can see, we have the final proof right there. So the trick with these questions is just simply pretending that the forces are acting in a straight line, again, due to the pulley being frictionless. And once we know it's in a straight line, it's very easy to form equations, such as these ones, to kind of see what's happening. And then you'll see some similarities between the two equations, and then we can just use simultaneous equations. This one we used division, but up here we just use simple addition. And so you will see this quite a lot in physics scholarship. You will see a scenario where you have to prove some ungodly equation. Like this at first glance seems, I will admit, quite impossible, but usually the scenarios are quite easy to distill into a simple format like this, which you've seen plenty of times before. And then it's just a simple case of going through the process to eventually solve the equation.